definitions and things like that. I want to go through that super quickly. Hopefully you don't need to write anything down. Hopefully you can just watch. I'm just waiting for this to buffer a little bit. Seems like there's having some focus trouble. There it goes. All right. And so again, hopefully you're following along on page 31. For most of this class, we're going to say momentum here. We're just going to use mv. Notice it is a vector. It's mass times velocity. The units are going to be kilogram, meter per second. Okay, it's a goofy unit, whatever. All right. Now, there's also going to be a term, I believe I use capital J for impulse. And that's going to be the change in momentum. And I usually use change in momentum of one object. As we work through today, you're going to see there's some problems where we have multiple objects and then sometimes where it's just one object. So I'm going to try and keep that clear whether I'm talking about momentum for one object or momentum for all objects in a system. Okay. And then there's force. You guys know an equation for force. What is it? F equals, what's the standard way to write it in physics? F equals, what's A?
Acceleration.
Okay, what does it relate? How does it relate to velocity?
E squared over R.
No, that's for circles.
Oh, no, never mind.
dv dt in general, right? Okay, that's true. For certain problems, you're right. But in general, dv dt.
Okay, I just misunderstood.
Yep, yep. What if mass was a constant? You could bring it inside, couldn't you? What's mv? Momentum. So it turns out this is approximately equal to and I'm going to use a delta t there. All right. So sometimes we will write impulse as in a different way. And this is all kind of summarized on that page in there. So force, momentum, impulse, time are all related. When we're talking about momentum, though, usually we use it in the context of collisions. Delta T is usually called the collision time. It's the time in which two objects are touching during a collision. That took about a millisecond for my hand to hit there. Maybe it was 20 milliseconds, right? When this marker bounces off my head, it's in contact with my head for a tiny amount of time. Maybe 50 milliseconds. I don't know. Something like that. Okay? But the idea is if we want to learn about things like the force from an impact, we could analyze the motion. We could analyze the mass and its velocity before and after. That would give me the change in its momentum. I could watch the video carefully and analyze how many frames it was in contact with my skull. And from that, I could learn about the force. Cool? Class dismissed? Or should we do a few examples, perhaps? Just maybe. Right? Like, in theory, that's the whole thing. All right. I want you to look on the next page. 32. Conservation of momentum is discussed there. I'm going to derive that very quickly. This is the other part of the derivation, and then we'll be off just doing practice all day. So you can follow along with the derivation and not have to watch me. Not have to write anything. I apologize. Newton's third law. A great law. The force that I exert on you is equal and opposite direction of the force that you exert on me. A on B, B on A. Equal and opposite. Good. How does this relate to momentum? I want to underline this right here. If I'm exerting a force on one, I'm changing the momentum of one. Right? Forces on one are going to change the momentum of one. All right? And that's going to happen for some amount of time. Well, similarly, there's going to be this minus sign right there. And maybe I should make that stand out just because I think it's an important minus sign. Okay. The force on one is related to its change in momentum over time. Now think about this. We're doing this problem where the marker hits my skull, right? Who touches who longer? Does the marker touch my head for more or less time than I touch the marker? Equal. That's why I didn't bother to put subscripts down here. Do you agree? If I touch the board for 1 minute, the board is touching me for 1 minute. Man, I don't want to sit here for 1 minute. So let's just call it delta t's cancel out. Is everybody cool with that? So now check this out. I'm going to move this one to the other side. I'm going to get a little bit lazy here. Does everybody follow me here? The change in momentum of one plus the change in momentum of two is equal to 0. Well, that's basically saying the change in momentum of the 1-2 system is equal to 0. This is saying no change. Agreed? Well, that's the same thing as P initial of the system equals P final of the system. Got it? When an initial equals a final in physics, that's a conservation law. We say momentum is conserved. All right? Well, there's a few caveats to this. Strictly speaking, this was assuming these are the only forces that exist. When this marker hits my skull, are there other forces that exist on the marker? What are they? What's one that jumps out at you? mg. Here's the thing. As long as the collision time is really short, as long as delta t really tiny, this is true. Here's the deal. If the time that it takes to collide with my head is small, gravity doesn't have enough time to make a significant difference to the calculations. Yes?
With friction?
Yeah, so that's what's interesting. So if there's external forces, so that's actually the next thing. Or if the force external is approximately 0, delta t can be long. Let me give you an example. Suppose you take a satellite and you send it towards Venus, and it takes about 2-3 days to go around Venus, or maybe 2-3 hours. Well, out in space, there's no air resistance, so the external forces like friction are negligible. So then, even then, if the collision takes 2 days or 2 hours, it's still valid. So basically, as long as one of these two conditions is true. So if you had friction, but the collision time was super short, the friction doesn't have enough time to change it that much, it's negligible. Or if those external forces balance for some reason, it's also negligible. Let me show you an example of that. In this case, think about these two objects. Are there forces acting on these two objects right now? What are they? mg and the normal force. Don't they balance? So in this case, the external forces are negligible. Now, when these things collide, it takes a little bit of time, because I don't know if you can see this, it takes a little bit of time for this to spring and then bounce back. But hopefully the amount of work done by friction during that time interval is so small, we're going to ignore it. Cool? Is that good enough on your friction question? Yeah. All right. Whoops. Come on. So, things to notice. Okay. Right there, under there. 3 things to notice. Conservation of momentum is essentially a different way of addressing Newton's third law. We're going to use Newton's third law in this conservation of momentum form and figure some stuff out. Momentum of individual objects could change, but those changes should balance. If this one goes up in the I hat, this one had better go down in the I hat. This goes down in the J hat, etc. This would go up in the J hat. Good? But the net change of the system, as long as these assumptions, these are pretty big assumptions here, we need to have one of these things to be true. Good? Now, in practice, look at the bottom of page 32. How are we going to use this thing? In practice, if we want to do problems, we need to first see, is it valid to use this approach? And let me explain kind of big picture where we're at in the class. What's kind of the first thing we learned? We learned what? Sig figs, then vectors, then what? Kinematics. Kinematics. After that, we did 1D and 2D kinematics, then what? Forces. Kinematics we kind of hit in there. That was kind of, yeah. But do you remember we did forces? Yeah. What did we do after forces? We did circular motion forces, but it's still forces. We did friction, still forces. What? Energy. Work and energy. And I'll throw in power in there. We didn't do too much, but a little bit. Now we have this new concept, momentum. We have 4 tools for approaching physics problems. And now we're starting to get to that point where they all, like kinematics could involve force if you use a force to get an acceleration, right? Or, right, maybe you use the acceleration from kinematics, so there's a little bit of overlap. Forces appear in both work. We see forces appearing in momentum in the impulse equation I wrote a minute ago. All of these things are interrelated, but generally speaking, while not always true, this we use if A is constant, right? Those are kind of the easy kinematics problems. Or we did separation of variables if A not constant. Am I still on or am I off, Alan? Can you tell?
You're still on.
Okay. Just barely? Okay. Forces, right? We can do FBDs here. And we did force equations. And sometimes we did problems with friction, inclines. And then what else did we do in here? Force, we did circular motion a lot. Okay. Here, a lot of the variables that we solved were like F, A, and M. Those are the things that kind of related to those. Obviously, there's many, many other things. Here, this was usually when we had speed. Do you remember that a lot of the energy problems had speed in it? Or we had force times distance equals work with an angle. So this is the stuff basically that's on test 2, these 2 lines. Now, momentum is going to apply when we have collisions. So to be clear, we used these when it was one block moving around. And we see it's a different technique that we haven't been doing a lot of. We haven't done a ton of collisions. To be fair, you could say, well, didn't we have some problems up here where they hit a spring? You're right, that was a collision. We had a block collide with a spring. It turns out that's a special type of collision that happened to conserve energy, and that's why it was okay to do it in the energy chapter. But now we're going to do all types of collisions. Good? The hard part as you get more and more tools is knowing which tool to grab for which problem, because they start to look a lot similar, right? All of these could have force in them somewhere. So just because a question says force doesn't mean you should do that. However, on test 2, coming up next Monday, if something's talking about acceleration, that's a pretty good sign you better do an FBD, right? And if something's talking about speed, that's a pretty good sign you better do a work energy problem. That's not always going to work because, for example, circular motion, v squared over r, sometimes A and B are related. Enough on that?
Yep.
Okay, that's just kind of big picture of where we're at. Make sure you know the right tool to grab. So that's step 1 of this problem solving. Go back to page 32 at the bottom. First, should I use conservation momentum or not? Is it a collision or an explosion or some kind of change of shape with negligible external forces? Or is the collision time small? Then what are we going to do? Draw before and after pictures, just like energy. We're going to list some equations, read for some keywords, and turn the crank. More on that in a minute. Okay? That is the entire lecture. The rest is practice. I want to start with a simple problem with numbers and units to get all that stuff right. I want to start simple and then rapidly speed up. So let's go back and do 9.1. You've got the definitions right up above. We're going to do 9.1 together. I'm going to erase, catch up. Any questions before I erase? All right, take a look at 9.1. I'll catch up. I don't know if I said this or not. Chapter 9 is not on your test on Monday. Got it? But in order to, right, we have to do this. We're going to be doing practice tomorrow on chapters 5 through 8. But we got to keep going or we're never going to get through this class. So sorry if I didn't make that clear. This is not on test 2. This is on test 3. We're always going to have to do that to kind of be right around the test, be transitioning ahead. Okay. 9.1. There's a big rock embedded in the earth. There's a ball headed towards it. Happens to be almost perfectly horizontal, so we're going to assume it's perfectly horizontal. Wait, isn't it going 6 meters per second? Yeah. Mm-hmm. I think I'll just use 2 sig figs. I don't really care. Okay, and then what's the mass of this? Is it 0.075 kilograms?
Yeah. Yep.
So that's 75 grams. That's realistic for a bouncy ball. We're told it's in contact with the wall for 50 milliseconds, I think. 0.050 seconds.
Yeah.
That's the collision time. So that's 50. This is a realistic problem for once. 6 meters per second, maybe like 12, 15 miles an hour. That's totally reasonable to think you could throw a bouncy ball horizontally at a wall that it has about 100 gram mass and it's in contact with the wall for this short of a time. This is realistic, okay? So I'll call this before. Or you could call it initial, or you could call it stage 1, any of those things. After the collision, it's going this way with what, 4?
Yeah.
4.0 meters per second. All right. Before we go on, I want to do just a quick check. Gravity is going to act on this for 0.05 seconds. I'm just curious what kind of change that would give. Let's say gravity was acting on it. Just side note. Whoops. how much would gravity affect the velocities? Well, let's just do G times delta T. What's 9.8 times 0.05? Punch it in real quick. I'm going to grab my calculator as well. I'm assuming it's tiny. 0.049. So that's maybe about 10% here. It's not completely negligible. Gravity would have an effect on this. Do you agree? But we're going to assume this effect is negligible. We know we're making a mistake, but that mistake is pretty small. That's good enough for me. Are you okay with that? That's what I mean. If the collision time is smaller than this, it's really truly negligible. This error might be, so really what's happening is the ball is not going to be going perfectly horizontal. It's going to be bouncing off and then be going slightly downwards afterwards. Agreed? Because gravity would, but come on. If this is 4 and that's 0.49, if I tried to draw it to scale, it would change it like that. Notice it's approximately correct. We're just assuming it goes purely horizontal. Is everybody cool with that? So that's what I mean. We're always making these approximations to get the job done. And then you do trial and error on a real object to try and make your life match or something. All right. I'm going to say 10% error. Not too bad. Okay. So that's the first step, is to always think, is the collision time small enough for this to be negligible? A. I want P initial. What's the equation? It's up at the top of the page.
P equals M times V.
MV. It's not jealous. That would be envy. Okay, so what am I going to get? I got my calculator here. Punch in some numbers. No, oh, there's my calculator. We got our mass. We got our V. 0.075 times 6. I got 0.45. What are the units going to be? Remind me.
Kilograms times meters per second.
Yes, they're just weird, ugly units. Kilogram. Make sure you put that dot in between. Good. Does that look good? What do you think? Exactly. This is a vector. This is a vector. Is this a vector? No. What direction is it? Initial. Negative I hat. So I'm going to put a negative I hat on that. Does that make sense? That's the momentum. Momentum is a vector. It's not like energy. We have to include the I hats or something like that. All right. And this is for the ball, so I'm going to put a little subscript B there. That would be mass of the ball, the initial of the ball, etc. This one's going to be what? 2/3 of it. So what direction is this one? So I'm going to put in the plus sign. You don't have to, but I'm just going to do it just to kind of emphasize the direction there. Everybody cool with that? We usually put the plus or minus on the right end of the term and the I hat out at the back end. I'm assuming we're supposed to get delta P of the ball next. Is that right?
Yep.
Change in momentum. What's it going to be? Exactly. That's what I was looking for. It's not 15. It doesn't change by 15 here. Look, you gotta just trust the math. It's P final ball minus P initial ball, and there's no shortcutting it. The minus of the minus gives me 75. Are you good on that?
No.
No, why not?
There should be an I and the direction, so in this case, positive.
Exactly. Good. Nice. Change in momentum is a vector because momentum is a vector. You got it. All right. What's part C?
That was part C.
Oh, whoops. D, I mean. What's another name for change in momentum? Remind me. Impulse. There was an impulse provided to the ball. Okay, E. Average force on ball. So I want force average on ball. How do I do that?
Delta P over delta T.
That's it. That's what we're doing. Delta P of the ball over delta T. And I think we know that crap, don't we? Yeah, delta T. I'm gonna search my brain and guess it ends up being what, 15 or something? Is that right?
15.
It helps to have done this problem a few hours ago. Which direction though? Look at this picture. What direction was the force on the ball? It had to be this way. Do you agree? Do our calculations match that? To the right. We're good. This is all being consistent. 15 newtons. That's a reasonable amount of force. When you think about it, that's equivalent to a 1.5 kilogram mass. Now think about that. That's a pretty large force on a 75 gram ball, but it only happened for 50 milliseconds. So this is kind of strange, but maybe you have some intuition for this already. Why is it not fun to run into people or have somebody throw something at you? It hurts, right? Why does it hurt? Because there's such a small collision time. Even though the change in momentum may not be so big, the force gets blown up, right? So if you have a longer collision time, if somebody, I don't know, right? If somebody gives you a hug instead of a punch to the face, usually the hug feels better. I don't know, unless you're into boxing or something. I don't know. Whatever. So, yeah. All right.
You don't want to be in a clench either.
That's true. Yeah, okay. Okay, so clearly I know nothing. Let's focus on what I do know here. The average force on the earth. Oh, we're getting spicy now. I want force average on the earth. What's that going to be? What object exerted the force on the ball? The rock. What is the rock connected to? The entire earth. So think about this. This giant cliff is basically part of the earth. The earth pushed on the ball that way, 15 newtons I have. What's the force on the earth? Negative 15 newtons. I have, right? Earth pushes on ball that way with 15. Ball pushes on earth this way with 15. What's the change in the earth's velocity? How could I get the change in the earth's velocity out of this? How does this relate to velocity? force average on the earth, how could I get velocity involved?
You could substitute the impulse is equal to force.
Exactly. We're just going to work backwards now to learn about the earth. Isn't that cool? So by learning about the ball, we can actually learn something about the other object that it hits. This is really cool. All right, force average on the earth is delta P of earth all over delta T, which tells us delta P of the earth is force on earth times delta T. But what is momentum? That's going to be mass times delta V. Now, maybe that makes sense. Do you agree? Take a second. Do you agree delta P, I could have factored out the mass of the ball? Take a second to look at this, right? Well, the mass of the ball is in here. So the change in here could be, I could factor out this and it would be mass times the change in velocity. Agreed? I'm going to just flip this backwards in an attempt to squeeze it all in here. And now I've run out of room, so I'm going to finish right here. Not good style, I know. Just bringing that up here. The change in velocity of the earth is the force on the earth times delta T divided by the mass of the earth. Well, the mass of the earth is about 6 times 10 to the 24th kilograms. If you're wondering how we get that, wait for chapter 13. We'll explain how you get the mass of the earth later. It's not obvious. Okay, but we got 15 I hat 0.05 seconds. Mass was 6 times 10 to the 24th. I'm going to leave off the units because I have no space. But when I do that,
Shouldn't it be -15 if it's on Earth?
what was it? Yes, you're right. There was a negative. That's absolutely right. Thank you. And so there we punch in some numbers now. I think this, you can tell it's going to be like 10 to the minus 24th or 5th. 15 times 0.05 div 6 EE 24. 1.25. Negative meters per second I hat. Oh, wait, I forgot the times 10 to the minus 25th. That's kind of a big mistake. Meters per second I hat. Sorry, that's the crappiest. I just wanted to point out, this is what I kept saying earlier. We don't really notice the earth move. It's not that it doesn't have an effect on the earth. It's that this is tiny. For reference, a hydrogen atom is 10 to the minus 10th meters. A hydrogen nucleus is 10 to the minus 15th. So what is this? About 1 billion times smaller than a nucleus. So in 1 billion seconds, this would change the Earth's velocity enough so that in 1 billion seconds, it would move an additional nucleus width. That's ridiculous, right? Insane. Good enough? All right. When you have a large mass, we get this very, very small velocity change. Okay. At the bottom of page 31 is another example. I kind of mixed that up and threw in some aliens telekinetic chemical link. That sounds great. What's that?
No more zombies.
None. Well, we might have zombies for a few more weeks, but I do know there is one problem where I say no more zombies. But we'll see where that is. I think we get Frankenstein instead. Yeah, so dumb. All right, 9.2 and 9.48 are good problems to look at. Okay. In particular, I want to look at 948 really quick. Just skim over there. Where is that thing problem? There it is, on page 51. I know this seems crazy, but I really did know a guy named Chris Moon who got emails from a different guy with a moon that had 3 O's in his name. Really weird. Anyways, but that's not the weird part. The weird part is, can you imagine doing a lab like that first talk where you made a video of some crap and plotted Y versus T? In fact, doesn't this look a lot like your plot? Remember that? The coefficient of restitution talk that you guys saw where the thing was bouncing? Imagine this. Imagine you take a video of anything in the real world and you could get its velocity as a function of time or its position as a function of time. From that information, you could get the pieces you need to do these calculations. And that's how we can figure out the forces acting on real life objects by just making videos of them. Isn't that wild? To me, that's kind of interesting. Enough said? You can do that one later when you're getting ready to practice for the final. So for some reason, I thought that's a better question to review for the final necessarily than midterm 3. All right, moving on. There's a classic question everybody asks next, or maybe you've heard of it. What if everybody goes to the North Pole and jumps? How would that affect the Earth? Well, let's think about it. That's problem 9.3 if you care. So I've written it out, but I just want to think it through. Maybe we'll think it through this way. Come on. Basically, imagine everybody is an elite NBA level jumper, okay? And everybody on the planet goes to the North Pole and is shaped into a box. So here's the mass of the Earth. Give me a number of people on Earth. Estimate.
7 billion.
Okay, so 7 times 10 to the 9th people. What's the typical mass of a human in kilograms? How about pounds?
So usually a pound is about 2.2 kilograms, so that's about
50 kilograms?
Yeah, I'm 100 kilograms. I'm kind of maybe even more now.
70?
COVID, right? But yeah, so let's say everybody's as big as me. That's probably an overestimate, I hope. So we'll say everybody's 100 kilograms. What's the total mass of everybody on Earth? Mass of the humans. Yeah. 7 times 10 to the 11th kilograms. What was the mass of the Earth? 6 times 10 to the 24 kilograms. 10 to the 12th times bigger. What is that? Trillion or 13, right? 10 trillion times bigger. So even if we all go crazy and jump straight up in the air at maybe 5 meters per second, that's pretty crazy to me, right? If we all jump up there at 10 miles an hour, that seems pretty fast, but maybe reasonable. Hell, let's say we do it at 50. Let's say we all jump straight up in the air at 100 miles an hour. Well, there'd still be, this would be moving downwards 50 meters per second times the mass ratio here. It'd be like 1 over 10 to the 13th. It's still 0. Got it? Or approximately 0. Did that make any sense?
Yeah.
If this mass is 10 to the 13th times smaller, it's right. Maybe I could say it like this. How about this? Mass of the humans times the velocity of the humans should equal mass of the Earth, and there's going to be a negative sign because it goes the opposite way. Velocity of the Earth, right? That's what's happening in this problem. Or I guess maybe I should write it like this. This is a pretty small mass too. So, right, you got a tiny mass with a big velocity. That's going to be the opposite of this big mass. Remember when I was throwing the, we did the hovercraft experiment?
Yeah.
Same thing, same thing. Enough on the Earth and jumping off the North Pole. All right. Okay, let's do 9.4 now. 9.4. starting to get a feeling for momentum a little bit, maybe the units, the directions, etc. There's a lot of minus signs in this chapter, so you got to always be watching your minus signs. Good. 9.4. I like to get a feel for this. I'm going to look at it first. Imagine we have something like this. We have two carts and they're going to hit each other, right? Is this showing up, Alan?
Yeah.
Okay, and then, oh, whoops, there's a couple on here. The idea is we can do different things with these and they're going to bounce in different ways. Now we can run this exact experiment in just a minute, hopefully, or a very good approximation to it. And we're going to see if we can model this equation correctly using our strategy. All right. So before we try and do it exactly perfect, let's do the math. Let's do the boring part first. And then let's see if our equations seem to match up to reality. Okay. 9.4. There's a before picture and an after picture. We got these carts. The wheels are actually just there to basically allow us to think of these as sliding without friction, right? So we use these little wheels. This is effectively a block that's sliding with negligible friction. That's what the wheels do. So this was object 1. This is object 2. And afterwards, they collide. One is still moving this way, but maybe at some different speed. I want to be clear about something. In particular, V1 initial, V1 final, and V2 final, we are assuming are speeds, not velocities. They're V's, not V's. Did that make any sense at all? I'm just trying to clarify that this is together, the speed and the direction makes a velocity. Agreed? So together, the picture shows a velocity, but that I just want to specify as a speed. This is a really annoying thing in this chapter. You constantly have to be reading. Did he ask for speed or velocity? Do I need to think about the I-hats and J-hats, or just is it just a speed? Okay. Now in this problem, we are going to try to follow the problem-solving strategy at the bottom of page 32. In particular, we said normal forces and weights balance. So as a result, external forces are negligible. We can ignore them. Is everybody okay with that? The normal force and the weights are going to balance. That's why it's okay to use conservation of momentum. Because those external forces are negligible, or because the collision time is small, that's when it's okay to do this. Not overthink it, let's get to work. Usually we don't write system because we're lazy. We'll just say P initial equals P final. In this problem, is anything moving up and down? Is there any J hat crap anywhere? No. So what I'm going to do is I'm going to change this to P initial in the X and what immediately drops out?
The I-hats.
The I-hats. And so typically we never really write the I-hats. It's a lot like kinematics where you say anything that's going to the right, we assumed had a plus I-hat on it. Anything that was to the left had a minus. Up was positive J-hat, down is negative. You know what I'm saying? So just to be clear, this is another assumption I just stated. We're assuming we use a normal coordinate system unless there's some good reason to do otherwise. Sometimes there is, but we're assuming a normal XY coordinate system. All right. Well, in this case, I'm going to get mass 1, V1 initial, plus mass 2, V2 initial, equals mass 1, V1 final. What's V2 initial in this problem? 0. Was this one initially at rest or something?
Yep.
We were told somewhere it was at rest. Okay. It's going to help me take care of this one. Man, I'm digging these markers right now. Nice and fresh. I don't know why. What are we supposed to figure out?
Final speed.
Final speed of M1. Which variable am I looking for? V1 final. This is what we're trying to find. I would divide every term by M1 and they don't completely cancel, right? And so we're left with what's called the mass ratio over here. So this is what I was talking about on the planet Earth, right? It's always the mass ratio that ends up affecting things. The ratio of your mass to the other object's mass. Good? This is very typical where we see a mass ratio survive. Good observation. Good idea. Nice move. So now, just rearranging that, what do I get? Well, I don't want to screw this up. So I get V1 final equals minus this other term. There's my speed. That was part A. So far, so good. Next, part B. Plug in the numbers. What do we got? 6.51. Okay, let's not worry about sig figs here too much, right? What was it, 3.8? What are you going to get? Then negative 1.6.
Yep.
Are you worried? What is V1 final supposed to be again?
A vacuum, sir. Forgot the I.
Oh, so
It's supposed to be a speed, but it's negative, right? Here's where we have to do a little thinking. This answer is correct. And you know that it's, so what's happening here is, I'm going to say it this way. Answer for speed came out negative. Actually moves opposite direction drawn. We're going to use this technique a lot, where we take a guess. Basically, I was guessing when these two things collide that they both keep moving that way. I was wrong. That's okay. My answer turned out negative. So what's really happening is the before picture was fine. We have a block going this way, hitting a stationary, 1 and 2. And then after, 1 is actually moving backwards when 2 moves forwards. That's what the negative sign means right here. This minus sign means all of this. Did that make any sense at all?
put it in the object to stay around, because otherwise what happens?
No.
So,
Yeah. And in fact, so think about this. 2, it's on rollers, right? And we can do this. So it's going to move forwards. Now, why don't we get, well, what is V2 final, right? In this case, weren't we told that? 3.8. So we're expecting the big one's going to actually be moving faster than this one, but this one's going to be moving backwards a little bit slowly, right? Now, it's not always going to be perfect because I can't always get this exact set of numbers, but let's try some experiments and see if the basics look right. Did I address your question a little bit? Yeah. Okay. So now in this case, I don't know if you know this, these carts are about 500 grams. Each one of these is 500 grams. So this is, wait, I want this to be, this is the heavy one. Okay. And I want to have a light object hit a heavy one. Now, to be fair, it's not easy to do this exactly the same as the numbers, but we should see one important thing. When the light object hits the heavy one, sometimes it bounces backwards. This looks pretty much like the numbers we just saw. Obviously, we don't have, we could measure this with video, and we're not doing that because that would take a while, right? But again, it looks pretty reasonable. Now here we could get more complicated. What if they're both coming together, right? There's a case where sometimes this one will stop. And here's a classic one. If you've ever played pool, have you ever seen it where you hit the cue ball, hit another ball, and for some reason the cue ball just stops? If you have identical masses, that's what should happen. So if you have identical masses and there's no actual, and they're very elastic, more on that later. So I'm going to leave it at that. This is what let's go back to the board. Sorry, I'm getting excited. What have we just done? Let's look at your problem solving strategy because that's what you need to know how to do on test day for test 3. First, is it okay to use momentum? There's a collision, probably. Okay, but this is the real way to do it. Are the external forces negligible or is the collision time small? Next, what do? Draw before and after pictures, right? We did that. If you don't know what direction the objects go, just pick one and do it. And what will happen is, if you get a minus sign, opposite the direction drawn. If you don't get a minus sign, you guessed correct. This is true for bridges, where you talk about, I don't know if this bridge, if this strut on this bridge is under compression or tension. Just take a guess, draw it. So civil engineers use this all the time. Okay. Write down your momentum equations. In this case, we only had one direction, so the x. If it was two-dimensional, we could write separate equations for x and y. Good? Okay? Oh, watch out. I'm just going to show you something really quick. You know this, you're not going to screw this up, but I'm going to draw it anyways because I see it on test questions all the time. Let's say you had some velocity here, right? At an angle. Let's say this is theta. I think most of you would have no trouble saying Vx is V cosine theta, right? So obviously we're going to start using this when we split up our momentum into x and y. We're going to have to get the sines and cosines involved. But one thing you do not want to do, you do not want to write Vx cosine theta. This is wrong. Because the Vx already includes the cosine. You know what I'm saying? So when you're writing, be careful. Vx or V cosine, but you don't want to put both the x subscript and the cosine. Understood? Okay, more? Okay. We haven't said this yet. I did slip a little bit. Did you hear me say elastic a few minutes ago when I was talking here? Elastic is a special key word we're going to use. You see something in the problem where it says the collision is elastic. Elastic, bouncy. That makes me think that energy is conserved. Okay, like springs. You know what I'm saying? So this is a key word you're going to have to learn. Elastic in physics means energy is conserved. So to be clear, if you had a 2D elastic collision, I'm not going to do a lot of these, but you could write down how many equations in theory could you write down out of that? Probably not. What's conservation of momentum? How many equations is that in theory? One for the x, one for the y. In theory, we could even have one for the z direction. Ugh. We're going to stick to 2D. So usually this is going to be two equations for us, x and y. And then you could also write this. Right? So there's technically three equations for a 2D elastic collision. X and y momentum and an energy equation. So far, so good? And why am I mentioning that during this problem solving strategy? Well, maybe that extra equation helps you solve the problem, right? In theory, if you have three equations, you can have three unknowns. So if you have a problem and you're looking and you're like, gosh, I have three unknowns, check and see if it was an elastic collision or something. And then at that point, read, solve it. Good? Okay. Look at 9.5. Look at 9.5 really quick. Talk to your neighbor. Try and solve it. I'm going to draw it up. It's going to take me a minute. I want you guys to talk amongst yourselves and see if you can solve 9.5. School bus in the boat.
Schools have the same. The mass of the evidence is so small that it affects. Creating the same force, more negative one. Two powers so small compared to the plus. It's cool. still put. Gas station. Oh, one of those people. One of those sandwiches.
Someone wants to be,
Okay, what do you think? You got a bus and you got a bug. Which one's gonna have the larger force on it? The same, like Newton's third law. F argon bus is equal but opposite to F bus on bug. That's just the facts. Okay. Part B. So to be clear here, same magnitude. Opposite directions. That's easy. Same. How about part B? We're saying which one has the larger change in momentum. Which one's that going to be? Which one? Sorry. Bug? Same. Delta P over delta T equals delta P. They have the same collision time. There's a minus sign, right? The force is delta P over delta T. The bug is in contact with the bus for the collision the same amount of time, right?
and this is because mass is pretty much negligible, or,
Let's see.
I don't know, explain it at the moment.
I do. It's the next question. You'll see. And then we'll take our break after this, right? Okay. Part C. What does part C say?
Both objects flying bus accelerate, which acceleration has a larger magnitude.
So which one has the larger acceleration?
It changes direction.
They have the same force. It's not even that. Let's just do this. Do you agree? Mass of the bug, is it big or small? So its acceleration will be huge. That's equal and opposite to what's true about the mass of the bus. So what must be true about its acceleration? So it's not because it reverses direction. Now, that's pretty common when you hit something that's bigger than you. The bigger object usually wins. Yeah, so like if you ran into a car, you would probably go backwards too. Don't recommend trying that. But yeah, is that making some sense? Tiny mass, big A, equal and opposite to big mass, tiny a. Good enough? So here, I would like to summarize this way. Smaller mass has more acceleration magnitude. Got it? Okay, good time for a break? Let's do it. We'll come back and just start doing collisions all day. Do more and more practice. You know the basics at this point. You're just applying it. There's a lot of tricks, and I'm going to try and show you as many as I can in the next hour. All right, so I've got some fun stuff here to I've got a couple of fun demos to keep you awake every once in a while, so I'm gonna try and do one of them here. So here I have two spheres. Right, now I don't know if you can see these very well on this camera. Whoops. There they are. There are two spheres. I'm just gonna drop them, and I want you to watch what happens to these two spheres when I drop them. You see that one bounces and one doesn't? Okay, just look at it again. All right, and now I'm going to take these two spheres and I'm going to put them on here. I think this is the non-bouncy. Okay, you got this non-bouncy. It's that board. Now I'm going to do this the bouncy. Put this on here. Just enough to knock the board over. Why is that? When this bounces, let's say it's moving downwards with a speed of about 3 meters per second, and then it bounces up with 2 meters per second, versus this one, it's moving downwards with 3, and then it stops. Which one has the larger change in momentum when these bounce? They're the same mass. They're the same mass. If you put them on a scale, I think they're both 23 grams.
The non-bouncy one, I meant.
The bouncy one changes more. Now think, going from 3 to 0, let me say this with the minus signs. Going from -3 to 0 is a smaller change than going from -3 to +2. You know what I'm saying? When you reverse direction, you change momentum more than when you stop. Reversing direction causes a larger force. That's why this one basically stops when it hits the board. There's a certain amount of momentum loss there. The board has an equal but opposite momentum loss. Whereas this one, you're changing the momentum by more because you have to, oh, they kind of bounced a couple. That was cool. Anyway, so just remember that. When things reverse direction, they change more momentum than when they stop. Understood? Yeah. Side note, let's try my new prefix here. Here we go. You probably know this thing. This is called a Newton's cradle. It's mentioned in problem 9.14. It turns out this problem is often misexplained in physics classes, but it looks so cool, so I'm going to talk about it. The idea here is these are steel spheres. Now, when steel hits steel, you lose very little energy, right? So an interesting thing, if I just pull these all up, this is a lot like the two pool balls, where one ball stops and the other goes off, right? That's only going to happen in an elastic collision when you have two objects with the same mass. So a one-dimensional, right, it's basically only in the X, a one-dimensional elastic, steel on steel is super bouncy, even though you don't think about it that way. It's super bouncy. It's almost perfectly elastic. So we have 1D, elastic collision, same mass. One object stops, the other goes flying off. All right? Now, when you put all of these other spheres in here, the question becomes, if I raise one on this side, how many should go up on the other side? And we see one, but notice it's a little bit sloppy. Sometimes the smaller ones do a better job. And so if you're curious about this, you can read more about it in the solutions. And it turns out building large versions of these, like the one you see in the back out of steel pétanque balls. Pétanque is a weird French bocce game or whatever. Maybe it's Italian, I don't know. But pétanque is a name for a bocce ball-like game with steel spheres. Yeah, you can do this to your heart's content. This is kind of fun. Check this out. What if I do 4 on one side, 1 on the other? We see it starting. You could do all this all day, but you could argue, how could I predict the number of spheres that are going to move after impact? You could do a momentum and an energy problem and discuss that. But read the problem more if you want to find out about the subtleties involved and why that's maybe not the perfect way to do it, et cetera, et cetera, et cetera. Also, I think that something has to do with the size of the spheres, the time it takes for the collision to propagate through the entire chain will make this problem work, will make these work less and less well as the spheres get larger, because it takes more time for the collision to propagate all the way through to the other sphere on the other end. See, it's not perfect. If you watch carefully, watch this one right here. It moves just a little bit. Anyways, whatever. If you're curious and want to learn more, read about it. That's cool. All right. Let me go to here. I want you to open up page 34. Those are some fun. If you want to look at those demos after class, that's cool. Look at page 34. On page 34, I've outlined a bunch of different types of collisions. So here's a bunch of terms you're supposed to kind of learn, all right? I'm going to call these types of collisions because some of them are also explosions, okay? Now, when I do this, the first one you'll see is perfectly inelastic. The main property of a perfectly inelastic collision, two objects stick together. If it helps, let me show you one. Get this crap out of the way. Here is an example. Now, you may not be able to see this very well, but there's some Velcro right here. Some Velcro right, Velcro right here too. So the idea is, hopefully this won't spring out on me, they stick together. So notice, when we were doing a momentum problem, we'd have an M1 V1 initial, M2 V2 initial, but there's only one mass at the end and only V final at the end, right? So that's the main thing. If you have a perfectly inelastic collision, you're supposed to know, oh, the two objects stick together, there's only one V final. Good? Something like that. M1, V1 plus. Now, obviously, there might be minus signs, but you get the idea. There's basically one term on the right side. We already mentioned this. If something says elastic, we could use E initial equals E final. Okay. Next, inelastic. This is actually most collisions in the real world. Oh, thank you. Thank you. Appreciate it. Sorry about that. On Zoom there. So elastic, E initial is E final. Inelastic, E initial is not equal to E final. I'll say it this way. Some energy lost, delta E, is negative. Change in energy is negative. By the way, for this one up here, delta E is also negative. We're going to lose energy for both of these. So only when we have the elastic collision is the energy conserved. For a typical explosion, you gain energy. And let me give you an example of a simple explosion. All right. This is going to be a very low energy explosion, so we don't have to worry about anything. But, and so you might be thinking, what does he mean by explosion here? It means something maybe different to me than it does to you. Remember how I spring loaded this thing, how there's a spring inside of here? check this out. They exploded apart. That's what I mean by you could have something where you're storing energy inside of it. You push them together and they explode apart. Now, obviously, in this case, we could put different amounts of mass on these too. And so when something explodes, it splits into fragments. This is the simplest possible one. But notice the lighter fragment is going to move faster than the heavier fragment when they explode. Why? Big M, little v. Small m, big V when they split apart. Okay? So explosion sounds a lot cooler than it really is. It's just two cards with a spring. All right, that's fine. Now, what do you know about springs? What do springs conserve sometimes? Energy. So you could have an elastic explosion, depending on how the two blocks are separated. Now here, there's a lot of friction in that system. But if you had a really good spring, or maybe if we used some magnets, you could have an elastic explosion, and then E initial would equal E final. Now, to be clear, for all of these types of collisions, something is conserved. There's one thing they all have in common. P initial is equal to P final for the system. So it doesn't matter, but any of these topics, you can use conservation momentum. Sometimes, for these two cases, you can use conservation of energy. Sometimes you expect change in energy to be positive or negative, and sometimes there's only one term. Got it? At this point, we're going to do as many versions of these as we can with the time we have left. Okay, got it? Maybe I'll mention one last thing while I'm talking about energy, right? We talk about change in energy. Usually we're talking about, how would I say, is usually change in kinetic energy. Not always, right? What if we have energy in a spring or something? So that would be K final minus K initial. If I wanted a percent change, usually for me that's delta K over K initial. So if you hear me talk about percent change, I'm talking about the change as a fraction, and then we multiply by 100%, which is 1. So if you see these words in the problems, delta E or delta energy, change in energy, is usually just the final kinetic energies minus the initials. And the percent change would be divide that by K initial and convert to a percent. Okay with that? Percent change is, yeah. We need that in some problem. Just remember that we wrote that down somewhere. All right. Maybe I'll do one last problem here. Well, actually, yeah. Let's look at these. If you've got your workbook handy, look at 9.6 and 9.7. 9.6 and 9.7. And what you could see there is, notice I actually asked you to figure these things out, but I thought I might just show you the cases really quick. I'm going to leave these problems for you to do at home, but I just wanted to point this out. Which one was this? This is, I need this one. Okay. So the idea here is you could have two objects of equal mass, and let me zoom out just a little bit. Get this book out of here. This is what I wanted to point out. If you have two objects of equal mass and you have this type of collision, what type is that? What type of collision is this? It's perfectly inelastic. It's perfectly inelastic because they stick together. When you do this, you're going to double the mass, cut the speed in half. However, What if you have a light object hitting a heavier object? This is now 3 times the mass. Do you think it's going to lose more or less energy when you have a light object hitting a stationary heavy object? What do you think? It's not going to move back because it's not bouncing. It's not elastic. The other ones with magnets or springs in there tend to bounce back. So in this case, it's going to move forwards, but do you agree it loses a lot of energy? It's barely moving afterwards. On the flip side, no, not now. Come on now. Come on. Right from the last one, right? There we go. What if you had a bus, heavy object, hit a light object? Do you notice the bus losing a lot of energy when it hits a mosquito? It plows right through and you barely notice the difference, right? So we see that there's different amounts of energy loss. If you are curious, do the problem or read the solution. Got it? That's for 9.6. What if it's elastic? If it's elastic, got some big magnets on here, and as a result, they aren't even going to touch, right? And so the magnets are used to cause them to impact without even touching. Now notice there's actually a pretty long collision time. Watch how long the magnets are having an effect. Right, it's much longer than the marker. Well, not this hitting my head, but now that's all right. So, right, if you throw a ball at your head, right, it's going to impact. Hey, March Madness, 2 points, right? Oh, that's Velcro from the thing. All right, whatever. In this case, we discussed this a little bit already, but when I have 2 objects of equal mass, right, and it's an elastic collision, one of them stops and the other goes flying off. If I have heavy hits light, they both go off in that direction. The light one is not big enough to impede the progress of this one and reverse it. But if we switch the situation, light is moving and it hits a stationary heavy mass, that's when we see it bounce backwards. So if you're curious about that, that's 9.7. Good enough? Now we've done that kind of problem already. We've already done one example. Now you've seen them. So if you're trying to get a feeling for that, go back and watch this video. Next, I'm going to go 9.11. Let's do 9.11 next. 38. 9.11. I'll change up the camera after I'm done erasing. Remember, you've got the solutions to these. I'm going to try and fly through them. So you may need to read the solution, but rewatch the vid later. But I'd rather show as many of these cases as I can. This is the only day I get to show you examples of momentum. All right. Next time we start center mass, or wait, next time you have a test. That's true. Okay. 9.11. This is a little bit different. We're looking at a top view. 4. Block 1 going this way. And block 2 going this way. Maybe I should color code that, huh? I'll make this one blue. I don't know if the blue and purple shows up that well. Whoops, I promised I would change the camera. Let me do that. Sorry about that. That does not show up that well. Try green. Looks a little better. kind of faint. Okay, so we've got objects 1 and 2. So this is the truck with this mass M1, fine. So we're told M1, and we're told V1 initial. This is V2 initial. Two objects stick together. Final state. We're going to make some blob here. And they're going to move off at some angle. All right. When you have, imagine we're in a drone or a helicopter and we're looking down, these two cars, right? Do you agree that their normal force and their weights are balanced, just like the carts examples that we were just looking at? Right, the normal force would be coming out of the page and the weight would be going into the page, but they're going to balance. We're assuming they're driving on level ground. We're told that somewhere even. They're going to collide. Is it reasonable to use momentum here? It's chapter 9. Sure. Right? But right, if the external forces are negligible, we can do it. So that's fine. All right, in this case, we can use momentum. How many equations do I get? 2, because I could split this into P initial X equals P final X, and P initial Y equals P final Y. And by doing this, I don't need to worry about writing the I hats on this one. So and the J hats are implied on this one. So now this is different because we haven't done anything 2D yet, right? Okay. Well, let's do it. What's P initial X? What should I write down? Does mass 1 have any initial momentum in the X?
Yes.
Okay, what's the equation for momentum for 1? Mass 1, V1 initial. And I guess we're assuming a standard coordinate system unless otherwise specified. I'll draw it this time. Unless otherwise, right? There's no reason to not use a standard coordinate system here. So let's do it. All right. Should this be positive or negative I hat? Positive. What about 2? How much in the I hat?
None.
None. What's P final? What mass? Mass total. So I would write M1 plus M2, right? I need the total mass. Agreed? Because they came together. This is a perfectly inelastic. Perfectly inelastic. Okay, I need the X component of velocity. What's that?
V cosine phi.
Yeah. We're going to call it V final cosine phi. So far, so good? Let's do the Y. See if you can beat me to it. P initial Y equals P final Y. You try it, I'll try it. What's that? The final sign. Got it? All right. Hopefully that makes sense to you. Now, I know this seems a little bit silly, but I'm going to do one more step here. I'm just going to write down specifically what our givens are, because see how it looks like just alphabet soup right now? Like what things are supposedly known and what are not known. So let's make a quick list. It says the mass 1 is given. I'm just reading the statement and seeing what was given. V1 mass 2 is also given. Is V final given? No. What about V? It's not clear. Do you agree? I'm going to assume V final, V unknown. Okay, because it's not really clear if those are given or not. I bet we could figure them out. In particular, how many equations do you see? 2. How many unknowns? I bet we can do the problem. Agreed? Shoot. What if I wanted to get V final? What technique could I use? You could square both equations and add them, and the sine and the cosine would drop out. Remember that? What if you wanted to get the angle? Let's say I wanted to figure out phi. What would a ratio do? You can take a ratio, and what happens to V final?
It cancels out,
It drops out, and you get tangent phi. You see what I'm saying?
and then it becomes arctan.
Yeah, you get arctanus unmixed, right? Are you guys do you want me to keep working on this or not? You good with this? I feel like you could solve this one, but there's one extra little piece here. So I just want to point out, I'm pretty sure you could solve this and this and this and this. We could, let me put the question marks on here. We could find these two things. We got 2 equations, 2 unknowns, done. What is this other parameter that's a given? D, that's a different piece. It says in the problem, after the 2 objects stick together, they slide off along the ground distance D before coming to rest. So this is a side problem. After collision, side view, we see 1 and 2. They're moving some speed, V final. And they slide over here and come to rest. What type of problem does that look like? You could do kinematics and forces, and that would work. Is there another method? We know about V. We've got one object sliding around. Do work, energy. Couldn't we do K initial plus U initial plus work equals K final plus U final? What force is doing work? When you have an object that slides and comes to rest, it must be friction. The work done by friction should cancel out the kinetic energy. In particular, I'd expect, well, I'm going to set my reference level right in the middle. Comes to rest, the kinetic energy minus the work, or plus the work done by friction, which is negative. So you either say minus friction or whatever. I should be careful. It's kinetic energy plus the work done by friction, which is negative, adds up to 0. And you could just crank out and solve for some parameter like mu or d. Well, d is given, so I bet you could find mu. Is that what we're supposed to do? Take a look at part F. What are you supposed to do? Determine mu. Now, I didn't do much of that problem, but I would rather focus on the setups. Is that okay? You got the solutions, you could do the rest at home?
Yeah.
Okay, should we do another one then?
Yeah, sure.
So this is, I do want to emphasize 2 things here though. In 2D, make sure you split up the X and Y, watch your minus signs. In this problem, of course, I do the easy one, right? But in a real problem, couldn't these also be angled too? And if these are angled, you might have sines or cosines on each of these terms, agreed? So that's one thing, the way I might mix this up is make everything angled. For example, look at the next problem, 9.12. You could do that one at home. Right, there's one where there's more angles. What else? This is tricky, but check this out. If you can get this, please listen up right here. During the collision, use conservation momentum. If elastic, you can also use conservation of energy. After the collision, when they're moving around as a single object, do energy. Got it? So usually during collisions, momentum. After or before collisions, use energy. Let me hammer that point even more. Go to 9.9. 9.9. Okay. It's gonna seem a little weird. I'm gonna set something up. Just a simpler contrived problem I made up just to kind of help you think about this, when you should use energy and when you should use momentum. The goal of this problem is to think about when I should use momentum and when I should use energy. Okay, now look, in this case, I have a cart. It's going to slide down the hill and hopefully not fall off the table. Ooh, let's see if it hits the hand sand. Okay. This seems like a simple enough problem. I want you to look at 9.9 in your book right now. Do you agree I've drawn pictures for you kind of showing this now? I'm going to draw those up on the board. But again, I'll show you one more time just to get a visual of it. Ready? Here it is, one more time. You're sliding down, hits this thing and it moves off. Okay, let's look at the stages of this problem. Stage 1, it's sitting on top of the ramp. This is going to be, okay. This is stage 1. I'll do stage 2. I can't go down the page completely, so I'm going to do stage 3 over here. Stage 4. In all of them, there's a ramp. This one, the block starts right here. Now we're assuming it slides with negligible friction. In reality, it has little wheels, which reduce the friction to near 0. Now there's also a cart here that it lands on, right? So in this one, the block reaches the end of the ramp and it's moving this way with some speed v. Afterwards, it's sitting on top, and this thing's moving with some other speed. I'll call it v prime or whatever. I don't know what I called it. Oh, did you see how I did this? I called this v1 equals 0. I called this v2 equals I don't know what. So that means I'm probably, instead of calling this prime, I'll call this v3. Then over here it comes to rest. Well, it took me a while to get there, but. So that's the table. Jeez, this takes a while. Okay. Between stage 1 and stage 2, what type of problem should we do? What do you think? Is it momentum or energy or both or which? Energy. It's one block sliding around. There's been no collision yet. So I would say E1 equals E2. How about between stage 2 and stage 3? What type of problem does that look like? Momentum. There's a collision. So I would say P2 equals P3. What type of collision is this? Yes. They stick together. And then between stage 3 and stage 4, what type of problem does that look like? Energy is one mega object sliding around. This is a common kind of overarching theme we see in some physics problems, where you'll do conservation of energy on one stage to learn about the speed before impact. And then you'll do an impact problem, which means do momentum. Then you maybe see that final speed being used, and we're converting this kinetic energy to thermal energy in this case, work done by friction. That's the big picture. What do you think? All right. Here's another classic example of that. Hopefully, wait, was I on the right whiteboard? Sure hope so. Oh, I was. Okay. Oh my gosh, sometimes this is really insane. Let's do this one here. I'm just going to show you another case. The classic one you'll see. Alan? Yeah, thanks, boss. All right. Poor Alan's reduced to my video editor. Okay, I'm taking a mass here. Sphere. I'm going to shove this in here. All right. And now, what is this thing? Probably can't see it very well, but inside of here, there's basically a hole, and that will catch the sphere. All right, so let's just do this. Right, so you can see there's a spot for the sphere to land in there and get caught. All right. Now, when I launch this thing, we see this swings up to some maximum angle, and I forgot to record it. Let's say it swung up to about right there. That looks about right. But no, I could just do it again. Now what I'm going to do is I'm going to set the angle to 0, and this little angle, is that showing up, Alan?
Yeah.
Okay, 1, 2, 3. What's that?
You forgot it was the angle.
What's that? Did I forget the angle?
Yeah.
Oh no, I got it. I got it. Oh, you can't see the angle?
Or I mean, it wasn't like that before. That's what.
Right. But now hopefully you can. Sorry. Yeah, it's good. It's good. Point being, let's just summarize it this way. I shoot the ball into here and this swings up to some angle theta, right? What stages would you draw? If you were going to try and describe this one, right? Oops, I'm on board 6. We drew stages for these different problems. What stages would I draw to analyze this problem? Well, let's take a look. Okay, what's one thing you might draw? Okay, just before it launches. So there's a spring in there and there's a ball and it's pressed up against, and here's my catcher.
You pull that back when you spring on those.
Maybe I'll call this V2 because it's the stage. You agree V1 is 0, it hasn't launched yet? Give me a stage 3. What's that? The collision. After the collision, here's my little spring gun here. The ball is now in the catcher. Is it at rest? Did it move, or was it, after the ball went in there, was it still moving? Think about it. If something hits you, right, you're going to move backwards, right? Whoa, you recoil. So during the collision, there's some final speed here, V3, right? Otherwise, it wouldn't have swung up to some angle. Gee, what's stage 4? The highest point. When we see this, what type of problem might you do between stage 1 and stage 2? Energy, spring, velocity, we don't have to worry about GPE. So I'd say E1 equals E2. We're ignoring friction. Maybe there is friction with the wall. You can account for that with the work done by friction. Okay, how about between stage 2 and stage 3? How about between 3 and 4? Energy. It's one object swinging up. What's the height it goes up? Remind me. What's this height? Remember we derived that and I said you better know this? Hint. I think that's enough said. Better know that. It's on about half of the tests that are coming on Monday. I don't know which ones, right? If you look at the practice test, you'll see I use this a lot, right? Just giving you a heads up. Okay. Now think about this. What did we measure in this problem? We measured the angle was about 40 degrees using this technique. You could probably get the radius. We could probably get the masses. What could we use this to figure out? The velocity. This is called a ballistic pendulum. You shoot a gun into a block of wood, see how high it raises, you can figure out the speed of the bullet. This is how you can figure out the speed of bullets without catching them in your teeth, which is my usual method, but I'm trying to quit. It's a joke. Hey, on the bright side, we only got 15 minutes left in class, so let's have a ball. A basketball that's overinflated. That's problem 9.13 or 14. Take a look at it. All right. Take a look at 9.13, will you? Oh my goodness. Oh, whoops, I got you. It's a, the camera's looking right at you. Sorry about that. It's only gonna take a second. Yeah, there you go. We got a basketball, we got a tennis ball. Whoops. Let's put the basketball right here, and I'm gonna drop it. We got the tennis ball. Now, if I was really, really good at this, what I would do is I would drop the basketball and have it bounce up, and then have the tennis ball moving down to meet it. So basically, drop the basketball a split second before I drop the tennis ball, like that. Okay. Now it turns out that situation is very similar to just doing this. Right? All right, got it. So my question to you is, let's see if we can analyze. Do you agree there's a collision here, even when I drop them right on top of each other? when I drop, it's the same as this bouncing down, coming up to meet this one. Let's look at 913 real quick. I'm gonna erase real quick. You guys can read while I'm erasing. 913. We're going to overinflate the crap out of that b-ball. Why would I want to do that? If I overinflate the basketball, what's that going to do to it?
It'll be almost like perfectly elastic.
It's almost, okay, so we're doing this. I'll just say elastic. Okay. So we're going to assume that it's going to conserve energy. That's why we're doing this one. And as a result, it's not exactly true, but the basketball is about 3 times the mass of the tennis ball. We're going to drop them from the same height. And as a result, if we drop them from the same height, and the basketball's perfectly bouncy, we expect they should be moving about the same speed when they hit each other. Is everybody okay with that? Remember, the tennis ball is moving down, the basketball came down just a split second before, it bounces and it comes back up. But if it's perfectly elastic, it's going to come up at the same speed it was going down. Part A. What is the speed when they hit the ground? I'm going to do a quick energy problem. If I drop this ball, what type of energy does it have initially? mgh. If it's up, are you okay with that? Sorry about that. I didn't specify that. That's my fault. But does that make sense? It initially has mgh. I'm going to be super lazy and say the work done is 0 and not explain why, because we're running out of time. The final energy just before impact is kinetic. What's the relationship between the height and the speed? V equals the square root of 2gh, or I could write it this way. H is going to equal what? V squared over 2g. I just want to keep that in mind. If we know what height we drop it from, we should be able to figure out the V. Likewise, if I know the speed, I should be able to figure out the height. Cool with that? This is not the main focus of the problem. If you want to understand this more, right after class, I'll explain it. But basically, just know that if you drop a ball from a height h, we expect its speed to be square root of 2gh. Good. So in theory, I could know these two numbers. That's what I'm trying to say. Is if I measure the height, I should be able to get these numbers. So I should know m, I should know v, I should know v, and I should know 3. So these are knowns. That's my point. So far, so good? Good. We know those things. Afterwards, this is the bigger object. We might expect it to keep trucking along. This is the smaller object. we're probably gonna expect that one to go upwards. I'll call this one V1 final, and this V2 final. I suppose I could call it V3 final, but whatever. Objects 1 and 2, whatever. It's elastic. There's a collision. What equations can I write? What's one equation you can write if the collision is elastic? Momentum, because you can write that for any collision. Smart. Now, do you agree this one is in the Y? What's the initial momentum in the Y direction for the tennis ball? I would write negative mv because it's going in the negative j hat. Does that make sense? It's speed v, but there's a negative j hat, so there's an implied j hat right there. All right. Next, how about this one?
It's 3mv.
Equals. They're both positive. What drops out in this particular way of writing it?
Masses.
You divide each term by m. On this side, I'm going to get 2v. On that side, v1 final. Now keep in mind, the whole point of this stupid problem was to say we should know what v is. If I measure the height accurately, I know what v is. So I have one equation, two unknowns. That's not a good place to be. I need another equation. Give it to me. What's the other one? X does nothing for me. Do you agree? There's nothing in the X. What's the other equation?
E initial equals E final.
Yeah, it's written right there. Do you see it? Elastic conserves energy. Well, this was momentum, right? So I can write, okay. In this case, what's the energy for this one? 1/2 mv squared plus 1/2 3m v squared. Notice I'm not going to try and figure it all out in my head. I'm just going to write the formula, and then if it's mass, I stick in m. If it's 3m, I stick in the 3m and simplify it in the next step. What drops out? What does every term have in it? Oh, sorry, I went fast. I'll wait. I'll give you a second. Sorry about that. Do you agree that's just kinetic energy of 1 plus kinetic energy of 2 initial equals kinetic energy of 1 final plus kinetic energy of 2 final? What drops out? The halves and m. The numbers don't. Now, out of all this crap, what do I get on this side? 4v squared, if I'm not mistaken, right?
Yep.
Just keep an eye on it there. 3. I think that's what we get. Now, to be clear, we have two equations. I have this one, and I have this one. How many unknown parameters in theory in a real life experiment? 2. Right? Because I could get the v from the initial height that I drop it. So we're pretending that v is a given. We're assuming that v is known for this problem, right? I want to learn about the final velocities. How could I do that? What should I do next?
For the top equation, maybe divide 2 onto both sides so that we can plug in V.
We gotta solve for one in here and plug it down there. Now, remember, we don't want to get rid of V, that's our known, right? V is the thing that we're pretending we know. So what's one of the other things that's easier to get rid of? V1 final equals 2V minus 3V2 final, right? Yep, I can plug that in here. Let's do it. Race you. These are generally the most time-consuming calculations in the whole class. So if you're wondering which calculations take the most algebra, it's these. Elastic collisions. They're just annoying. I'm going to FOIL that crap out. 4V squared, right? First term squared. Second term squared is going to be, that's going to get rid of the negative. And now I get 2 times the cross term. The cross term is 6 negative, and then double that, which is 12, and then I got a V2 final. Did that in my head. Let's check that again. 2V times negative 3V should be negative 6V V final. And then I got a double. Yeah, that's right. Did that make sense what I did there? Just boiling it out. You see anything cool? What drops? Yeah. So it ends up dropping anyways. Isn't that interesting? So it turns out, Mark, if we had done that other way, it probably would have worked equally well. Normally it wouldn't, but in this special problem it would have. And out of the rest of this, what do I get? 0 equals my dog? Oh, that's true. My dog is 0, but that's a different equation. I have a dog named 0, believe it or not. It's been a long day. I don't care. I'm having a good time. How would you approach that equation? Can you guys see it at all? Or is it, can you, okay. I'm gonna write it up here. Let me put it up on the other board, all right? We're just running out of room. Give me a sec.
Is that 2V V2 final?
Yeah, I'm gonna write that up here. So out of all that, I get, and I'll change the camera in just a second. Just getting it down. Does that help? Is that better? So there's the equation we have. How would you approach this? What could you do?
Take out one of the V finals and
Factor. And I know, remember I mentioned sometimes factoring is the way to go. You can also take out a 12, right?
Yeah.
Well, how many solutions are there to this equation?
2.
2. What's one of them?
0.
V2 final equals 0. What's the other one? Now think. What were we talking about here? We're talking about these two moving towards each other. And then you're telling me afterwards there's 2 solutions. One of them is the basketball stops moving and this one goes up. So that's this solution, right? The other one is this is moving down with speed v. This is moving up with speed v. And then the basketball continues moving with speed v and the tennis ball goes up. Which seems more realistic? Will the basketball stop, or is it going to keep moving with no change to speed? If you hit something, should it affect your speed? Yes. This is wrong. Basketball should stop moving. Isn't that crazy? You wouldn't see this if you didn't factor it. Now, here's the deal, right? This just is not realistic because if you hit something else, you've got to slow down, right? When this basketball is moving up and a tennis ball moving down hits it, it has to slow down. You know that is a fact. So let's look at that again. And I know it's time to go, but let's look at this one last time. Well, let me just show you this really quick. I swear this is it. This is the correct answer. Well, I could plug that in. Notice V1 final equals 2V. If you go back and plug it in, the basketball should stop moving and the tennis ball will move twice as fast. That means it should go how much higher? If you double the velocity, what happens to the height? What was our equation?
V squared over 2G.
It should go 4 times height initial. So when you drop this, did you notice the tennis ball hit the frickin' ceiling? We saw this happening in the demonstration. When you drop this, now the masses are not perfect, and that's why the basketball still moves. But when we do this, the basketball effectively drops to a very small velocity, and the tennis ball gets this massive increase in momentum, and it goes and hits the ceiling. Yes.
Shouldn't it be H equals V squared over 2G?
Yes. What did I say?
You wrote it as V squared over G.
Oh, yeah. There's a 2G. Thank you. That means over here. Let's get that fixed up. You're absolutely right. There it is. You're right. Okay. Oh my gosh, did we finish this? Oh my goodness. Phew. You guys should do the following problems. Put a star next to these, will you? You got to get the hell out of here, but listen to these problems. 915. This is page 40. Page 40. We haven't done any explosions yet, right? So do 915. What up, Dom? You got the bomb problem, 917. And then you got 917 and a half is weird. And 923. Yeah, if you could do those, you're in pretty good shape. There's others, right? But if you could do at least those, that'll get you rolling. And then you can do as many of the other ones as you need. Everybody cool with that? Sorry for running over, but I appreciate the extra time. If you want to do any of the demos, the Newton cradle or the basketball, go for it. Thanks for catching that typo.
That one's the basketball stops with some elastic.
Yeah, this is really perfectly elastic, and one mass is 3 times the other. If you ever go to some toy stores, you'll see this where they have bouncy balls, where one bouncy ball is exactly 3 times the mass of the other ones. And if you do this with bouncy balls, you could really, this works.
So the bus and the fly was perfectly inelastic.
Correct.
Stuck to it. That's
Yeah.
why the bus didn't.
Yeah.
Well, it slowed down a little bit, but it kept on going.
Right. It's, in that case, the bus is going to slow down, but it's so little we don't notice it. And then there's an engine connected to it, which helps it speed back up and account for the loss. Right? The bug is probably millions of times less mass. So that's why the bus has a millionth of the change of velocity. So it's so small we don't notice it. Good? Yeah. It's funny, there was a 4-story staircase in my old physics building, and we would do this 2 bouncy balls, and we could hit the ceiling 4 stories down. But if you missed ever so slightly, this thing would be coming at you hella fast, and it would like hit you in the face or whatever. It's pretty fun. Oh, I should stop the live stream now, before I get sued by EIU.